Let's learn about Lewis structures. So in my last video, I talked about Lewis dot symbols, which is a similar idea, but you're just doing it for an element, right? You're showing how many valence electrons an element has and arranging them in dots going around the outside of the element. Now, Lewis structures is how we show the bonding for molecules, right? So these are molecular compounds, so there's covalent bonds, and we're showing the bonding of all the elements in this compound. So let's make up an example and learn how to do this through example, okay? Let's take something like NF3, okay? So I'm gonna write out NF3, and our first step is to find out how many valence electrons there are in the entire compound. So just like I taught you in the Lewis dot symbol video, you're gonna look at the group A column number, right? So nitrogen is in group 5, and fluorine is in group 7A, right? 5A and 7A. And so those are the number of valence electrons for each of these elements. But we have to take into account that there's 1 nitrogen and 3 fluorines. So the way I like to write this out is I do like a coefficient here of the subscript. So how many nitrogens are there? There's 1. And I'm going to multiply that by the fact that each nitrogen has 5 valence electrons. So it's just 1 times 5. But it's nice to show our work so we know what the heck we did here, right? And then there's 3 fluorines. So that's going to become my coefficient here. And it's 3 times the fluorine atom is in group 7A. So that's 7 valence electrons. So it's 3 times 7. And then we just do that math, okay? So we have 21 plus 5. That's 26 valence electrons. 26, and I like to use this symbol. E minus is an electron, and then I put a little V in front for valence electrons, okay? So basically, we have to find a way to bond these atoms while satisfying their octet and only using 26 valence electrons altogether, okay? Now, typically, the element in front is usually going to be the central atom. There are some exceptions, so make sure you guys stay to the end because I'm going to go over the exceptions then. But for now, let's just stick with this. There's 1 nitrogen and 3 fluorines. So the 3 fluorines are going to be bonding to the nitrogen. Nitrogen is also less electronegative, so that kind of indicates that it's going to be the central atom again. So let's go ahead and draw this out. So we have a nitrogen, and it is bonded to the 3 fluorines. And a bond, just represented by a line, is 2 electrons, okay? So basically, we already drew 2, 4, 6 electrons on the page. And so we have 20 left over, right? Because I just drew 6. I have 20 electrons left over in order to give all the elements octet, if it's possible. And remember, what octet is basically the desire for elements to have 8 valence electrons. Again, there are exceptions here, but for the most part, the elements in Lewis structures, they're nonmetals, and they want to have the noble gas configuration or the electron configuration of the nearest noble gas. Noble gases are in group 8A, so they'd like to have 8 valence electrons. And those can be either in a bond or as lone pairs, okay? And I like to personify my elements that they want to have 8 valence electrons. It just kind of helps to think about it that way, right? But another way to phrase that is that they're more stable when they have a noble gas configuration, and that's why they form molecules to make these bonds so that they are more stable, okay? So let's take a look at this now. We're going to start off by giving octet to the outer atoms, to the terminal atoms here, and then we're going to see what we have left over and see if we can give the central atom octet. So this fluorine already has 2 electrons. It wants 8, so it's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So all the fluorines have octet right now. And so that's 8 times 3 is 24. And that's how many electrons we used already. Now we have 26 to play with here. So 26 minus the 24, we have 2 electrons left over. And if you look at the nitrogen, it already has 2, 4, 6 electrons. It would like to have 2 more. 2 more would make it stable, right? And so we're going to take the remaining 2 electrons and put them on the central atom as a lone pair, okay? So we go boom, boom. That's it. We're done. That is the Lewis structure of nitrogen trifluoride, okay? So let's do another example. and we'll keep coming across new ways of looking at things as we go, okay? Or new circumstances that make it a little more complicated. So let me think of another compound. And as I'm thinking about that, guys, if these videos help you, please give a like, follow, share, save them so you can review them again later. It does typically take more than one view to really get these things internalized. And make sure you do the practice problems. So like maybe when I write out a problem, pause it, give it a shot, and then watch that clip in order to see if you did it right or not and learn the proper way to do it. And then, by the way, if you guys would like to go above and beyond, you can check me out over here and you can patronize me. That really helps me continue to make these videos for free. So let's think about another example now. And let's just do something like oxygen gas, right? So oxygen gas is O2. And so there's only 2 atoms here. And so there's no central atom, right? We just have to find a way to bond these 2 things together with however many valence electrons we have available to us and try to give them both octet. Try to let them both have 8 valence electrons, whether they are in lone pairs or as covalent bonds. So we're going to draw our, well, actually, let's calculate that first. Oxygens are in group 6A, so they have 6 valence electrons. There's 2 of them, so we have 2 times the 6 is 12 valence electrons we have available to us. So let's take the oxygens and let's bond them to each other. So that's already 2 electrons. So now we want to try to give them 8 each, but only use 12. So let's just see what happens here. Let's just say I gave one of them octet. I go 1, 2, 3, 4, 5, 6. So, and then that's 7, 8. So that's got 8 already, right? So I have 8, and 12 minus 8 gives me 4 left to play with. So I only have 4 left to give to this other oxygen. Now, if we look at this one's happy. It's got 8 electrons, 8 valence electrons, but this one only has 2, 4, 6. That's not stable. It wants to have 8 valence electrons. And so how can we give them both 8 and yet not exceed the amount that we have available to us? Well, what if they just shared 2 more electrons? What if this oxygen allows this oxygen to share 2 of the electrons that it's hoarding to itself, the way that we drew it, right? So basically, we can't add anymore. I can't just, invent 2 more electrons because now it doesn't add up to the 12 here, right? Now we have 14 on the page. So I'm going to take 2 of these electrons. I'm going to take these ones just to make this look pretty and symmetrical. Those 2 electrons, I'm going to redraw them as a bond in between them. Because remember, a covalent bond like this is 2 valence electrons. And so now we have 2, 4, 6, 8 on this oxygen, and this one also has 2, 4, 6, 8, but altogether we have 2, 4, 6, 8, 10, 12 valence electrons, which is the amount that we had to play with in the beginning. So the point is, we want to satisfy their desire for octet, but while only using the amount of valence electrons that we have available to us. So let's keep going. Let's do another example. Let's do something with a charge just to add a little layer of complexity to this. Let's do something like NO3 minus, which is nitrate. And so NO3 minus, this is nitrate. That's a polyatomic ion, a polyatomic anion that you may have to memorize for your course, depending on if you have a sheet that gives them to you or not. But anyways, the point is, our first step, we're going to calculate the number of valence electrons that it has. So there's 1 nitrogen, and nitrogen is in group 5A. So, and by the way, you just look at your periodic table to figure that out, right? So if we look over here, that's group 1A, 2A, 3, 4, 5A. There's nitrogen there. And so that's how you know that it has 5 valence electrons. And let me rewrite this 5 because it's looking kind of ugly and I don't like it. All right, so we have 1 times the 5 valence electrons in nitrogen, plus there's 3 oxygens, so that's 3. Oxygen is in group 6, so it's times 6. But then we have a negative charge here. Now, remember, electrons are negative. They have a -1 charge. So how do we take something and make it negative? We just give it an extra electron. So if you have one more thing that's negative, an electron, now your net charge is negative. And if I gave it 2 extra electrons, then it would have a -2 charge, right? So this minus sign means I'm just going to add 1 more electron to my total count. If it was positive, I would remove an electron. because remember, we never change the number of protons that something has. That's non-negotiable, right? You'd be changing the element that it is, but you can add or subtract electrons. Those are the variable subatomic particle. So we're just going to add this one more electron, and now we have that's 18. What is it? 23, 24 valence electrons. 24 valence electrons to play with. And now we need to make sure all these things are bonded. Nitrogen is less electronegative, so it's going to be the central atom. And also typically, like I said, it's usually written in front. So either one of those methods usually work. Also, typically the element that's outnumbered, right? If there's only 2 different types of elements, there's 1 of these and 3 of these, you can kind of assume that that's going to be the central atom, all right? So all those things kind of line up there. Electronegativity, the way it's written, which usually does depend on electronegativity, by the way, and then also the quantities of each. So let's write down our nitrogen here, and we need to bond it to the 3 oxygens, right? Because this is a molecule, or in this case, it's a polyatomic ion, but you know, it's still, there's molecular bonds here, there's covalent bonds in between these elements. And so the next step is give octet to the outermost atoms, right? So we go 2, 4, 6, that's 8. 2, 4, 6, 8, 2, 4, 6, 8. Now let's count how many we have. That's 8 times 3, that's 24. So we already have 24 valence electrons on the page. The oxygens are all happy as a clam, right? They all have 8 valence electrons, but the nitrogen only has 2, 4, 6. And so what we have to do here is, just like we did with the O2, we have to share some electrons. We have to share more electrons. So because all 3 of these atoms are the same type of atom, we're just going to basically force one of them to share a lone pair as a covalent bond with the nitrogen. And because they're all the same type of atom, it doesn't matter. So we're just going to take it from this one, because that's what I felt like doing. And we're going to just make a double bond here. So now if we look at it, this oxygen still has 2, 4, 6, 8 electrons. These 2 both still have 8 each, and the nitrogen has 2, 4, 6, 8 electrons here. And so that's basically the structure here. And then when it has a charge, we do put it in a bracket, and we put the charge on the outside. Now, going forward, I'm not going to do it right now, but you do have to know about formal charges as well. And so to make this correct, I'm just going to put these formal charges here on each of these elements, that the nitrogen has a plus and these oxygens have a negative charge, but I'm not going to discuss that in this particular lecture. I'm going to do that in the next one, okay, guys? So make sure you subscribe or follow and keep up. I'm going to teach you about formal charges really soon, but I just wanted this to be technically correct. But the point is, this is how you get the Lewis structure for a compound like this, all right, guys? Let's do one more now, because this is where we get to the exception. And so something like hydrogen is in group 1A, and its nearest noble gas is helium, right? So hydrogen is here. If it wants to feel like a noble gas, or it wants to, you know, achieve the noble gas electron configuration, it only needs to gain 1 more electron. So hydrogen doesn't get octet, right? Oct is like the prefix for 8, right? Like an octagon has 8 sides. Octet is saying that the elements want to have 8 electrons, valence electrons. Hydrogen only wants to have 2. So we're not going to put lone pairs on the hydrogen. It's just going to have a single bond, and then you're just done with it, okay? So let's do something like HNO. I keep using N for some reason as the central atom, because I feel like there's a lot of interesting compounds with nitrogen as the central atom. So let's do HNO. And again, we're going to add up the valence electrons. This is in group 1, so we have 1 hydrogen times the 1 valence electron, plus there's 1 nitrogen times the 5, because it's in group 5, plus there's 1 oxygen, and there's 6 because it's in group 6, and that is equal to 12 valence electrons altogether. And so now let's bond these things together. So now hydrogen is technically, it is the least electronegative element, but because it only wants to have 2 electrons to feel like helium and be more stable, it can't be a central atom. So, because once you give it a bond, that's the 2 electrons, and it can't form more bonds, right? So we're not going to exceed 1 bond for hydrogen, so it can never be a central atom, okay? So we're going to put our H here, and then our N, and then our O. Nitrogen is less electronegative than oxygen, so this makes sense. And now we're going to give the elements octet. But remember, hydrogen gets a bond and it's done. You're not going to add lone pairs on this hydrogen. It doesn't want octet. It wants just to have 2 valence electrons to feel like helium, okay? Just to make that really extraordinarily clear. So let's give this oxygen octet and see how many electrons we have left over now. So it's 8, 9, 10. We have 12 available. So I have 2 more electrons. Let's give them to the nitrogen now. And then see, does it have octet? Well, it has 2, 4, 6 electrons on the nitrogen, right? The oxygen, we already just gave it 8. It's 2, 4, 6, 8. The hydrogen is happy because it's got the 2, but nitrogen is not happy. It only has the 2, 4, 6. So just like we did before, we're going to take a lone pair from the oxygen. It can no longer hoard it to itself, and we're going to force it to share and make this a double bond. Okay, guys? So now we have 2, 4, 6, 8, 2, 4, 6, 8. The hydrogen has 2, and altogether we have 2, 4, 6, 8, 10, 12 electrons, which is what we're supposed to have, and that is the Lewis structure for this compound as well. All right, guys? So I think that basically does it for this particular lecture. I'm going to talk more about the formal charges, and we're also going to get into resonance structures, all sorts of things like that. So again, guys, if this helps, please give a like, follow, share, save, and consider supporting me over here. And you can patronize me, and I'll see you guys in the next video.